Alrighty, for those who don't know, our lunch and learn sessions that we do are primarily built around talking about things that we've been doing or that we have done that hasn't been something that either everyone's been involved in or maybe there's an ancillary interest that goes along with that. Today, what we're going to be looking at is we're going to be looking at some of the design, manufacturing, analysis of the antenna that we are producing for this airborne application. So we're going to look at the purpose, what was done in order to build the thing to begin with, or what concepts and specs or lack of specs went into designing and developing this antenna, what we had to have in order to say, okay, yes, we can actually build this, and then put some of our mechanical folks on the hook for actually producing the thing that the math said go and make. And then where they said, hey, your walls don't actually have thickness. We need some thickness to, build, which is great. We're also going to look at some of the methods that go behind analyzing and actually synthesizing something that is it looks like a bunch of polynomial garbage to begin with. So what we're doing is we're designing and building an antenna, high gain, highly directional. Things that come into play there is if you want a lot of gain, you're going to have something that's fairly significant in size. The antenna itself is X-band. X-band is roughly in an 8 to 12 gigahertz range. We're going to be dealing with something that's going to be between 9.5 and about 10 gigahertz for the actual Q of the antenna. Now, the biggest thing that came up here was if we got to build it, if we want to design it and we want to build it, well, then we need to come up with whatever the methods are that go behind building the thing in the first place. And then the end product, how do we analyze and determine the end product is actually what we designed to begin with. So some of the things that went into it, looking at electromagnetics, building the waveguides, because this thing is basically a labyrinth of waveguides. That's all this thing is. It's a labyrinth of waveguides that allows us to put radiation out there in a known or knowable way. So some of the things that went into that was looking at materials. Well, what do they do? What do they do with boundary conditions? How do we go from one waveguide size to another? And as far as measuring it, we can't just take it and put a receiver, a radiator at the other end of the room and do this because the far field is very far off. We'll talk about far field and near field. So what is a slotted array? You see a picture here that is some concepts early on saying, okay, well, if we want to build a slotted array antenna, what are the basic operations that go into that? But really, a slotted array antenna is something that is going to put out radiation. It's going to be done in a way where it produces a linearly polarized type of radiation. Now, we talked about slotted arrays. Some people talk about phased arrays. There's a difference there. This thing gets tossed back and forth. Well, with a slotted array, we're talking about all the adjacent elements being coherent in phase. That's what allows us to have a nice pretty pattern out of the antenna. A phased array antenna can control phases of relatively spaced elements in order to steer the beam. There is some beam steering going on with this antenna, but we can't individually or in very tightly controlled patterns alter the relative phases of the radiation. So really, waveguide with holes. That's where the leaky waveguide thing comes up, is where we're pushing radiation down a pipe, radiation's coming out in a phase coherent manner. So what's allowing us to produce radiation that has a nice pattern to it? Well, if I just stick radiation out there and I talk about an isotropic antenna, something that's equal in all directions, or a dipole that's an omnidirectional antenna, well, I can have that, or I can have a patch antenna where I have some directionality to it, but really that's not something that, unless Dave and Tim really want to work with just a patch antenna, single element. I bet you guys could do it, right? Their processing come around all right. They want a really nice, tight, high gain beam that comes out of the antenna. So that's what we talk about when we talk about array factor. We have all those elements, more elements. If the underlying math was done right, we get a nice, tight, high gain beam coming down the middle, and that's what this plot represents here. We also get side lobes too, but we'll talk about that. Another concept we talk about are grating lobes. What we want is that we want that single strong lobe. So we want this center part of the pattern to be nice and strong and tight, which is what we see when we see this plot here. We see a representation of that. However, in reality, we're not going to get just this one nice monolithic beam going out. We're going to have something that's going to be plagued with side lobes. Now, talking about grating lobes, you know, depending on the relative spacing of the elements, they can be worse than others. We can get grating lobes that are actually equal to our main lobe. If we just go out there and pump out a perfectly rectangular array where we end up with the exact same spacing and there's no taper put to them, we will have side lobes in elevation and azimuth that are going to be just as strong as our main lobe, which would also be undesirable. Who wants to have radiation at right angles to what they care about, always pumping out power and coming back and creating all sorts of garbage and noise, and really a lot of false returns that we don't want to deal with. So grating lobes, something else that gets looked at now. Whenever you deal with something that's more than going to be one wavelength away from its relative, from its element spacing, then the problem gets worse and worse and worse. But the way we have it put together is that we're doing half wavelength element spacing and tapering to take care of that. Now, tapering. Has anyone not taken a good look at the antenna that we're working on? Rich really hasn't looked at it too much, neither Sarah. But there's a taper in the elements where we have a, as they're going along the rows, there's a taper going along one row. Now, the reason for the taper is to suppress side lobes. So you can see here on the right, we have a representation of side lobes that are, you see how close they are to the main lobe there? And then when we do a taper optimization, you see we're taking those side lobes and we're roughly suppressing them all down to about the same peak power from each lobe. And that's what we're doing with our antenna. Now, the way that this plot is set up, it ends up being repeating, so don't worry about the ones coming out at the 180 points there. Those don't actually exist. So when everything's suppressed down to zero is really the antenna that we're looking at for our design. Yes?
I guess I really haven't looked at the antenna that much. What are you tapering?
Oh, okay. Yeah, sure. Well, here's actually a prototype antenna that we worked with. And so we have the columns, we have the rows. Now this one is a uniform rectangular array, and we have them spaced and offset to get rid of some of the side lobes, or to pull some power out of the side lobes. Now on the antenna, the large array, we actually start out in the center with a larger magnitude taper that comes down, and it's using a Taylor series expansion to give us our offsets for that. Make sense?
It's the amount of separation. The taper is how much the slots are offset from the center line, which is the greatest in the middle and goes down to nil at the end.
It's probably hard to see on this one, but yeah, it basically, what you do is you really just have an absolute value offset from the center line. And so these are all equally offset. It just trades one side versus the other. Well, the taper that we're using in a large array starts at a magnitude and uses that expansion to bring that down to the end, rather than putting them all perfectly in a line, and which would give us some of the effects we see on that plot over there on the left side of the screen. So, like I mentioned, it's really just a rat race of waveguides that we're dealing with this antenna. Purpose of the waveguide is you're bringing radiation structured down a pipe, really. And what you're doing in that, once you deal with the insertion loss of getting into the waveguide, you're really not losing power once you get into it. And we're talking about kilowatts, tens of kilowatts of RF energy with this project. So we see different cross-section waveguides. What is the difference? Well, larger cross-section means lower cutoff frequency. All right. Something we're also doing is we're actually changing the speed of propagation of the energy going down the guide. Okay. Now, when we send energy down the guide, we can deal with multiple nodes in the electric field and the magnetic field that's coming down the waveguide. So for this, we're using a TE10. Our dominant mode in the waveguide is TE10. Now, something interesting is you can have higher order TE or TM propagation modes going down the waveguide. In a larger waveguide, you can push higher frequencies. You just will be changing transmission modes. Now, part of something else that you need to look at is you always have a cutoff frequency. There's always going to be a minimum frequency that can maintain a transmitting mode of propagation down a waveguide. For the one we're using that's actually feeding the antenna, that ends up being around just under 8 gigahertz is where the cutoff is of that. But there's a fair bit of insertion loss you're coming with at that point. Some other things that we looked at in the design were the boundary conditions. So we're going from one WR90 waveguide into a feed network that is different cross section, into another cross section that is the radiating portion. So we have these boundary conditions going from one to the other. And you'll see on the back plate of the antenna, if you go down to the machine shop, and you'll see that there's different tapers coming down the feeding to actually feed the radiating waveguides coming out of the antenna. That's what that's compensating for, is being able to transfer the maximum amount of energy for the aperture that we produced. And the actual slots in those apertures are about the same as the radiating slots themselves as far as their shape, but their orientations are different. Now this is the part that Rich and Sarah have had so much fun with, is how do we build this darn thing? The material we're using is going to be 6061 aluminum. I don't know, what does it come out? Just, not too soft, not too hard. It's like a T651.
It's T6.
Oh, it is T6, not 651. Okay.
I think
So it's a good general purpose aluminum. It's not one of these crazy unweldable, unbrazable type materials. It's something that shares a common characteristic, though, with all aluminums, in that if you're going to weld it or braze it or do anything, it likes to be extremely clean. Has anyone here ever welded aluminum or brazed aluminum? Yeah, it's not particularly fun if you've been done steel before, right? You can't just weld or braze dirty aluminum. It just, and it also doesn't have a lot of the telltale markers like steel does when it's getting hot. It doesn't turn red. It just collapses into a horrible slag heap, right? Yes. So the process that we're using in order to bond all the different pieces together for this project is called dip brazing. What dip brazing does is we take the actual pieces, we clamp them together or tack weld them together, and there's a donor piece of material put between layers. In this case, we're using a sheet metal that already has donor material on the clad. And it's actually dipped in a tank of molten salt, which melts the donor material and bonds them all together. So everything's preheated to about 1200 degrees, and then it's in its clamped position so it doesn't warp all to heck when they transfer it to the oven, or to the actual furnace. And they dip it in that furnace vat, melts the substrate material, they pull it out, they control cool it, and I'm hoping, well, at least the mechanical folks tell me it'll hook together, right? Everything will. There you go, without a doubt. That's without a doubt. So now something that's neat about the salt bath is it's preventing oxidation. So it's inhibiting oxygen from creating impurities in the actual bonding. And it's also allowing that material to flow, that donor material to flow. It acts like a flux. So when you solder, if you don't have flux, anyone had tried to solder without flux before? It's horrible, right? But when you have like a flux core solder, or you apply flux before you solder, it creates that nice, clean meniscus when you solder. Now, looking at simulating the antenna in order to come up with something for these mechanical folks to spend all their time and effort going forward and building, I wanted to be fairly sure that it was going to work in the first place. That seems important, right? That the thing would work in the first place. So some of the methodologies looked at behind this, you have different electromagnetic solvers. It used to be that universities would spend their time and effort and they would build these custom solvers using Fortran. They'd build clusters that would just solve weird electromagnetics problems. But then there came a time where companies started actually building solvers, and they started building tools that would let us understand and use these baseline boilerplate type electromagnetic simulators, so that everyone wasn't spending their time building a solver so they could do something before they could actually produce a design or simulate it. So in this case, I looked at some of the solvers. Now there's a finite difference time domain method, which is one of the differential equation solvers, not very easy to do something out of the box on your own. Method of moments is a very applicable way for this application of producing a good simulation of the radiation pattern. Anyone familiar with Emacs solvers at all? Okay. Well, you can, depending on the frequency in the application, you can look at them as a traditional electromagnetics type approach using Maxwell's equations. Method of moments is one that we do that with. Or you can do something in the very, very, very high frequencies, well beyond this, where you're taking an electro-optics approach, where you're looking at incident, reflection, return. There are some EO type things you can do at this frequency, but for determining what the pattern's going to be, it doesn't help us think about that in EO sense. Some of the tools, and I know that it's been kind of a crazy influx of different tools we've been using, MATLAB being a dominant tool that we use. We spent some time looking at Mathematica. Wolfram Alpha is wonderful to answer a few questions, but it's something that working in the language wasn't very easy in this project, and it also didn't provide me any good interchange with the other guys that were using MATLAB. Use MathCAD a little bit, but MATLAB's been the dominant tool for us, and what we did is really sort of a pick and poke type approach to method of moments to produce the overall radiation pattern we're looking for. At some point we're going to have to test this project. We're going to have to get this antenna back. It's getting ready to get crated and dip brazed. How are we going to go about doing that? Well, there's a difference between near field and far field, and it has to do with the actual cross section of spacing of elements in the antenna. For this application, the near field far field transition is between 115 and 116 feet. So unlike I was able to just set this up, and everyone's seen the little range I set up downstairs with this one, we can't do that inside with the large array. Besides to be a lot of other side lobe energy things that I'm sure we'd be getting kicked back to us. Now, when it comes to doing near field testing, you can test in the near field, however, your measurements need to be phase coherent. Your transmit and your receive, and there's some mathematics behind the reconstruction of it. There's some labs we work with that do that. It's really not the easiest way for us to deal with that for the folks that are already set up for it. So we do have a far field range that's about 500 meters long. Well, and where we're going to mount things will be about 400 meters of separation, which will get us well into the far field for this project. Near field is great, especially for space-constrained areas and getting good, quick answers because no one's going back and forth down the range to set things up. However, it does have some flaws because it is a calculated approximation. There is some error involved in it. We know that in RF energy, 3 dB is a factor of 2 with power difference. So let's say that I'm working in that log sense, and I'm shooting cables, and okay, well, it moved this way, but that bent this cable a little bit, and my overall loss of my chain is 1 dB different than I was. That can have implications for the reconstruction of the measurement. So what do we do to go towards designing and building this thing? What do we put into it? Well, the giant mill downstairs, that's really the only reason that we have that piece of equipment, is to build these large arrays. The CAD CAM packages that our mechanical folks are working with, SolidWorks, SolidCAM, those are their primary tools, and really working very solidly in the MATLAB realm for simulation is really all we've stuck with up to this point. The CMM arm, in order to figure out did what we draw that was a compromise of what's ideal, how does that compare to what we built? Because if what we wanted and what we planned on doing and what we actually made are 3 different things, we've got problems. How do we know if there is a problem, how do we know that's expected or unexpected? Well, that's how we're getting our as-built work there. Well, I went to a conference back in November, and that was one of the things that I'd say was very informative for me as to, well, do I even know what the heck I'm doing when it comes to designing this antenna? Because there's no one text, there's no one book, there's no one research paper or author out there that you're going to find IEEE Explorer, I don't care where, on the Google scholarly articles you look, there's not okay, here's your primer for building this antenna. So that was a good experience there. As far as doing the design and the work, nothing's really all that crazy as far as building the structures and the mathematics and the understanding of it. It's just a lot of really, linear algebra, ordinary differential equations, and understanding EMAG is really where a lot of it comes from. Hindsight 2020, probably would have bought one of the commercial solvers and actually gone through the simulation using one of the ones that does like the finite time, the FTDT type approaches. I'm sorry, FDDT approaches, just because that would have given us probably the ability to skip the step of doing the small array confirmation. It would have been 6 of one, half dozen of the other just for the one, but for ongoing alterations, probably a good idea to move to an actual solver tool. And Mathematica, I know I've talked about this tool with some folks in here, mostly some of the software folks. It's a great tool. I think it definitely has its place. I'd prefer a whiteboard over having a license of Mathematica in the end, just because it's sort of terrible to work with.